Welcome to the Processing Data for ML module. This introduction section describes the content of the module. This module provides a brief look at machine learning, or ML, and focuses on the ML lifecycle, which guides how data engineers and data scientists collect and process data for ML models. The module takes a quick look at general ML concepts and describes the activities that are performed in each phase of the ML lifecycle. You learn about framing the ML problem, collecting and pre-processing data, feature engineering, model development, and model deployment. You also look at the AWS infrastructure services that you can use to implement the ML lifecycle. Finally, you'll be introduced to other artificial intelligence, AI, and ML services that you can use to solve common use cases without needing a lot of ML knowledge. The objectives of this module are presented across multiple sections, each with its own video. The module wraps up with a sample exam question. This section introduces some foundational concepts about machine learning that will help to provide context to the discussion of data processing, which is the focus of the module. The Data-Driven Organizations module presents this contrast between the characteristics of traditional analytics and the field of AI/ML. With traditional methods, developers or data scientists write programming logic to represent a set of rules which are applied to data to get outcomes. With machine learning, the rules are not hard-coded. ML practitioners build a mathematical function that finds patterns in historical data and uses the patterns to learn how to predict outcomes when given new data. An ML model is a mathematical function that maps inputs to a set of predicted outcomes by using algorithms. When you start to build an ML model, the precise definition of the function isn't yet known. You start with a clean data set that's been prepared for ML and an algorithm that fits the data and the type of business problem that you're trying to solve. Algorithms are standardized methods that define the rules of the model. You might think of the algorithm as a recipe and the model as your cake. You use the algorithm with your ingredients, the data, and evaluate what it produces. How does the cake taste? And then adjust. You could use the same ingredients and a different recipe, and that might produce a slightly different cake or an entirely different dessert. It's the combination of the ingredients and the recipe that define the end product. The model is the combination of your trained data set and the algorithm that you use. There are three general types of ML models. The processing steps are different for each of them, but they all share the characteristics of using a data set and an algorithm to train a model to produce predictions. In supervised learning, a model uses known inputs and outputs to generalize future outputs. The examples throughout this module are based on supervised learning, which is currently the most common approach in use. Examples include identifying which transactions appear to be fraudulent. Is this fraud, yes or no? And categorizing objects into a group. This image contains a dog, a cat, or a bear. In unsupervised learning, the model doesn't know inputs or outputs from the historical data, so the model finds patterns in the data without help. Unsupervised learning is used when you need to identify clusters of related elements within the data. An example is grouping users with similar viewing patterns. With reinforcement learning, the model interacts with its environment and learns through trial and error to take actions that will maximize rewards. Self-driving cars are an example of reinforcement learning. AWS Deep Racer provides a hands-on way to learn about reinforcement learning. The service provides a 1/18th scale race car that's driven by reinforcement learning. Anyone interested can build models and see their results. The link to the AWS Deep Racer overview page is included in the course resources. The Data-Driven Organizations module introduces ML as a subcategory of AI. Deep learning is a subcategory of ML, whose algorithms use neural networks. A neural network is based on a collection of connected units or nodes that loosely models the neurons in a biological brain. With deep learning, a model can recognize patterns that are several magnitudes more complex than other ML models could. A deep learning example is a machine that can learn to play chess by playing against itself. Deep learning can solve more complex problems, but requires more compute power than other methods of ML. The idea of deep learning and neural networks has been around for decades, but the computing power that is needed to support it has only recently been readily available. Even in the 1950s, computer experts thought they could build intelligent systems, but computers weren't fast enough. Then, around the mid-1970s, researchers began using rule-based systems known as expert systems. This approach lasted for approximately 30 years. With these expert systems, academics got a good understanding of what computer-based intelligence actually was, but no production-ready applications resulted from this work. However, the evolution of neural network technologies continued until around 1998, when it became possible to start using data to make practical predictions by using what is now called machine learning. However, implementing these new approaches would require inexpensive storage of massive amounts of data. These approaches also required large amounts of computing power and a way to transfer data with very low latency between storage and compute. These capabilities didn't exist in a widely usable way until around 2007. The combination of more affordable cloud-based resources, coupled with the availability of graphic processing units, or GPUs, really pushed machine learning field into its modern era. GPUs were originally developed to power gaming applications, but soon became an important infrastructure component for ML solutions. By using GPUs, models can train at greatly accelerated processing speeds, which makes it more practical to use ML solutions for a wider variety of business problems. This slide uses a tabular data example to depict a few important concepts about the data that is used in ML models. A tabular data example makes it easy to see the components in familiar constructs. Labels and features appear as columns, and samples are represented by rows. A label, or target, is the outcome. It's also known as a class, dependent variable, or response. This is what you're trying to predict. A feature is an attribute or independent variable. It's also known as the predictor. Think of these as details that describe the target. And a sample is an occurrence of a target and its features. Here are a few key points to summarize this section. An ML model is a function that uses an algorithm and a trained data set to predict outcomes. Machine learning can be divided into three types of models: supervised, unsupervised, and reinforcement learning. Deep learning is a subcategory within machine learning where the models are developed on a neural network. This enables the models to recognize patterns that are much more complex than with traditional algorithms. This section describes a set of general steps that make up the ML lifecycle, which can be used to develop and deploy an ML solution. An ML application is a specific use case of a data pipeline. An ML solution will incorporate several types of ingestion, storage, processing, and analysis and visualization activities across the ML lifecycle. You won't be surprised to hear that the lifecycle that is depicted on this slide is iterative, and the phases in it aren't as well defined as the diagram suggests. The color selections on the steps segment the lifecycle into three main sections. The first two phases are about analyzing the problem that you want to solve and whether an ML solution can solve it. The third and fourth phases of the lifecycle are where data processing and modeling occur. And the last two phases are where the ML solution becomes operational. Note how the business goal drives the process and directly influences the metrics that you should choose to measure and monitor in the deployed model. The results then feed back in to determine whether the business goal is being met, and also feed back into model development. Checking that the model is serving the business need and making high-quality predictions is an ongoing process. The process data phase can be segmented into two steps: collect data and prepare data. The prepare data step is split into two closely related tasks: pre-processing and feature engineering. This slide identifies the types of roles that are involved in each phase of the ML lifecycle. Often a person might play multiple roles, or the work might be split up differently across the team. But generally speaking, a data scientist works with team members who know the relevant business domain to frame the ML problem. The data scientist is also involved in identifying the data to be collected. The data engineer is the primary owner of collecting the data and ingesting it through a data pipeline, which makes the data available for the data scientist to perform data processing on. The data scientist processes the data and develops the ML model, and then hands it off to the operations team to deploy and monitor in production. Often, an AI/ML architect will design the infrastructure and the workflow components that support completion of the ML lifecycle phases. Although a data engineer would not typically do model development or deployment, it's helpful to understand the process as it relates to the data pipeline that the engineer would build, and the amount and type of data that is needed. It's also important to recognize how feedback from the production model will come back through the pipeline. The skills and experience of each role in the ML lifecycle overlap. In fact, data engineers and ML engineers are two of the top 3 roles that transition during their career into an ML data scientist role. This module has sections about developing and deploying an ML model. The sections provide a brief overview of the tasks and environments that are required and offer additional context to data engineers about how pipeline data is used and processed in ML solutions. Here are a few key points to summarize this section. The ML lifecycle takes a business problem and frames it as an ML problem. The data engineer works with the data scientist to collect relevant data and prepare it for modeling through the steps of pre-processing and feature engineering. When the data scientist believes that the model is ready to be used, the operations team deploys it into production and ensures that monitoring is in place. Most phases involve multiple roles who have interrelated specialties. This section describes the activities performed in identifying the business goal and framing the ML problem. As described in the data-driven organizations model, it's important to work backwards from the desired goal and then determine how ML might be able to address the problem. You need to ask questions that help you to clarify what you're trying to solve. The problem statement is a concise statement that summarizes the answers to the questions presented on the prior slide. In the case of any company, they don't know why there's increased fraud, which types of insurance claims represent the most fraud, or where the most fraud is occurring. The ML solution could help them identify predictions so that their adjusters could address issues accordingly. Framing the ML problem is about using domain and data science expertise to determine how or if ML can address the business goal. The steps listed on the slide are all part of framing the ML problem. Most importantly, you need to identify what you want to predict and where you can get the data that supports your needs. As noted on the previous slide, part of framing the ML problem is determining whether ML is the correct approach. The left side of this decision flow highlights characteristics that might point you to using a business intelligence or BI or analytics solution instead of ML. The right side of the flow highlights questions that you need to consider before embarking on an ML solution, even if the business problem seems suited to the use of ML. The example scenario that is described here highlights some key outcomes of the phase to frame the ML problem. The data scientist has identified a data source that has enough relevant data, and they have identified an algorithm to start from. Here are a few key points to summarize this section. Working backwards from the business goal helps to ensure that the project is focused on outcomes rather than technology. Data scientists and domain experts work together to frame the ML problem to give them a starting point to collect the appropriate data and use the correct type of algorithm. ML is not always the correct approach. To rule out simpler approaches that might solve the requirement, rather than assuming that you need ML to predict an outcome. This section describes the activities that are completed during the collecting data step of the processing data phase. The collect data step in the ML lifecycle gets data from sources and moves it into a location where a data scientist can prepare it for ML. Consider the ML lifecycle in the context of the data pipeline concepts that this course has presented. A common ingestion pipeline for ML would be to use an extract, load, and transform, or ELT approach to load the data into a data lake from which most of the required transformations take place. As noted in other modules, the steps in the process and the roles that perform them will overlap and are typically iterative. The process includes cycles of discovery, ingesting, visualizing, and processing before the ML model is built and tested. Generally, the person who performs the data engineering would be responsible for getting the data into the pipeline and loading it into the data lake. The data scientist would be responsible for the majority of the required data wrangling. The two roles would collaborate on what data should be included and what types of structuring and cleaning are required as part of ingesting the data to support the model. The tools that are selected to perform data processing will influence where the responsibilities would be split. The considerations that are described in the ingesting and preparing data and the ingesting by batch or by stream modules apply to ingesting data to be used in ML models. The steps that are listed here reflect specific considerations for when the data that is being ingested will be used for ML applications. The step of applying labels applies to supervised learning models. The next two slides in the section that follows describe each of these steps in more detail. The Elements of Data module discusses the impact of bad data on analytics solutions, noting that it's better to have less high-quality data than to have a larger amount of data that cannot be trusted. Bad data is particularly harmful when fed into ML models, where it can be difficult or impossible to see the source of an error. If the model learns the wrong things, the predictions can't be trusted. A big part of the data scientist's job in implementing an ML solution is to make sure that the model is trained and tuned on clean data. The data scientist might perform the majority of the cleaning tasks as part of preparing the data to work with the selected ML algorithm. However, the data engineer needs to make sure that their processes to extract data from sources and combine it to ingest it into the pipeline follow best practices to ensure the veracity and secure transfer of the data that's being ingested. They should employ automated methods to validate data sets and audit the ingestion process. The data engineer might also be involved in tracing errors to their source and working with the data scientist to iterate on improving the quality of the data that's being ingested. In the fraud detection example, the data engineer would extract data from the relational database tables that were identified during the ML problem framing phase. The engineer has good information about the reliability of the internal data source, so they can focus their efforts on applying appropriate security and monitoring features to the ingestion pipeline. The dataset that is needed to build an ML model for supervised learning must provide enough quality labeled data to support both training and test datasets. The training dataset helps the model to learn the feature patterns in the data to make predictions. The test dataset helps the data science to validate the model and optimize the quality of the predictions. After the model has been trained and tested, it is deployed to production, where it runs against the production data source that you want to make decisions from. Feedback from production provides additional information about the accuracy of the model and might identify issues with the model or the quality of the dataset that you used to train it. The data engineer would not be responsible for deciding how to partition the dataset for training and test data. The data scientist would decide how to partition the data based on data characteristics and the model that's being developed. The source dataset must be large enough to account for the amount of data that needs to be labeled to train the model and the amount of test data that's needed to tune the model. The volume and quality of the available data for training and tuning are important factors in the quality of the predictions that can be made, and will vary within the type of data and modeling. Typically, 70 to 80% of the collected data is used to train the model. The remaining data is used to test and tune the model. After the model is deployed to production, the actual results can also be used to train and tune the model. Here are a few key points to summarize this section. The collect data step is similar to the ELT ingestion process that was described in the ingesting and preparing data module. A key aspect of this phase is to ensure that there are data sources that can provide enough high-quality data to account for training and testing the model. Labeling data is also a task that might happen during data collection. The next section talks more about labeling. This section describes the step of applying labels to the data that's being ingested. In machine learning, data labeling is the process of identifying targets in raw data, such as images, tabular data, text files, and videos. The process includes adding one or more meaningful and informative labels to provide context so that an ML model can learn from it. For example, a label might indicate whether a photo contains a dog or a cat, which words were uttered in an audio recording, or whether an X-ray image shows a tumor. Data labeling typically starts by asking humans to make judgments about given pieces of unlabeled data. For example, labelers might be asked to tag all the images in a dataset where "does the photo contain a dog" is true. The tagging can be as rough as a simple yes or no, or as granular as identifying the specific pixels in the image that are associated with the dog. The ML model uses human-provided labels to learn the underlying patterns in a process that is called model training. The result is a trained model, which can be used to make predictions on new data. A properly labeled dataset is used as the objective standard to train and assess a model, so spending the time and resources to ensure highly accurate data labeling is essential. In the fraud example, the labeling task would be to identify which samples in the ingested dataset were in fact fraudulent. This would enable the model to find patterns in the features that are related to that label and then predict which other samples are fraudulent. As noted in the slide, labeling might be done on images, text, or sounds. Amazon SageMaker Ground Truth is an example of a tool that makes it easier to organize and complete labeling tasks. You can upload a set of unlabeled data to an Amazon Simple Storage Service or Amazon S3 bucket, then set up a labeling job in SageMaker Ground Truth. In the labeling job, you can invite participants to be your labeling workforce and provide instructions and a UI that make it easy for the workforce to apply labels to each element in the job. Those who are invited to work on the labeling job receive a URL and an email invitation that takes them to the UI. Here they can label items that are stored in the S3 bucket that is associated with the job. The results from the labeling job are stored in Amazon S3, ready for additional preparation. Here are a few key points to summarize this section. Labeling is the act of adding useful labels to targets in the training data. Labeling can be done on images and video for computer vision, on text for natural language processing, and on audio files to categorize sounds. Tools, including SageMaker Ground Truth, can simplify the ability to give experts access to a dataset and apply labels to it.